In the next part, we're going to do exercises that have to do with continuity. So first we have to understand the definition of continuity. So we say that function f of x is continuous at x equals c if three things are true. First of all, f of c has to be defined. For example, c can't be a zero of the denominator. All right, second, the limit as x goes to f of c exists, and it has to be finite. We're not talking about infinite limits. And the limit as x goes to c of f of x is equal to f of c. In other words, the answer from A is equal to the answer from B. These two are the same. F of c and the limit have to be the same. Okay, so let's look at some examples. Okay, number one, we have 2x plus 5, f of x is equal to 2x plus 5. We know this is a line, and we're choosing c equal 2. And what we do is to determine if a function is continuous, we just check those three criteria, A, B, and C, see if they're all true. All right, so first for A, we're checking A. A is, does f of c exist? Well, f of 2 is equal to 9. So it exists. F of 2 exists. That's no problem. B says, does the limit exist? Okay, so the limit as x goes to 2 of 2x plus 5. This is a polynomial, so we take the limit just by substituting in. All right, so we're going to get the same thing that we got in the line above. And C asks, are A and B equal to one another? Well, yes, they are. They're equal. Okay, so that means that the limit as x goes to c of f of x is equal to f of c. Okay, so C is true as well, and we have yes, continuous. All right, let's look at number 2. Well, again, we have to see if A, B, and C exist. So A is, does f of c exist? Well, in this case, c is equal to 2, and 2 is a zero of the denominator, so the answer is no. Okay, because x equal 2 is not in the domain of f. F of 2 does not exist. So right away, we know we don't have to check B and C. A is not true. So right away, we know that our function is not continuous at c equal 2. Okay, let's look at number 3. So we're going to check A. Does, again, c equal 2, does f of 2 exist? Well, f of 2 is equal to, we use the bottom line for f of 2 because of this greater than or equal to here. F of 2 is equal to 2 times 2 plus 4, or 8. So yes, f of 2 exists. Let's look at the limit as x goes to 2. Well, since this is piecewise, we have to take the limit as x goes to 2 from the left and the right. So the limit as x goes to 2 from the left, plug in here, and we have 2 plus 3. We have 5. And how about the limit as x goes to 2 from the right? All right, just substitute it into here. And we have 8. All right, these are not equal. So we say limit as x goes to 2 does not exist. All right, so B is not true, so we conclude no, not continuous. Okay, here, again, we want to see if f of x is continuous at c equal 1. Well, without going through all the steps, let's first just look at it and examine it a little bit and see if we can determine what the answer is. Well, going through, just thinking about a, b, and c, f of 1 definitely exists. Right here, we just plug in here. Okay, that's a is true. What about the limit? Well, to see if the limit exists, quick way is we just substitute in 1 here and here. Okay, so if we substitute in 1 here, 3 minus 2 is 1. Substitute in 1 here, minus 1 plus 2 is 1. Okay, both the same, so it looks like the limit does exist. And a and b are equal to each other. F of 1 is equal to 1, and the limit is equal to 1. So yes, this one is going to be continuous, but we have to write it all out. So let's do that. Let's just write it out quickly. F of 1 is equal to, just substitute in here. So yes, A is true. B, limit. We have to take the two-sided limit. From the left, 3 times 1 minus 2. From the right, minus 1 plus 2. All right, these are equal. Implies the limit as x goes to 1 of f of x is equal to 1. Yes, limit exists, and these are the same. So we say limit as x goes to 1 of f of x is equal to f of 1. All right, all three are true, so we conclude yes, continuous at x equal 1. All right, let's look at number 5. A, how about f of 5? All right, f of 5 is 10. F of 5 exists. How about B, limit? Well, since f of x is equal to a polynomial except at one point, we can take the limit by just substituting into the polynomial. So the limit we get not from the second line, but from the first line. The limit is substituted into x squared. The limit is 5 squared. Limit exists, but notice these are not equal. So the limit as x goes to 5 of f of x is not equal to f of 5. Okay, 25 is not equal to 10. So we conclude that limit as x goes to 5 of f of x does not exist. So I think this is the first example that we're seeing here where A is true and B is true, but the two are not equal to one another. And this is a typical example of when that occurs. In this type of piecewise defined function, defined everywhere except for at a point, defined differently at one point, then typically this type of thing occurs. Okay, number 6. We want to check A, B, and C. And right away it's going to fail right here. F of 1 does not exist because it's a 0 of the denominator. Okay, f of x is equal to x minus 1 divided by x plus 1, x minus 1. Even though this does reduce, all right, it's still a 0 of the denominator written in this form. so right away it fails. F of 1 does not exist. All right, 1 is not in the domain, so we conclude not continuous. Let me just mention that B is true. So this is an example where A is not true, but B is true. The limit, what's the limit as x goes to 1? Now when we take the limit, we can do some canceling. So if we cancel these out, we have the limit as x goes to 1 of 1 over x plus 1, which is 1/2. So even though f of x is not continuous, the limit does exist. Okay, here we're looking at a definition. It says that a discontinuity is removable if the limit as x goes to c of f of x exists and is finite. So in other words, if part B is true, then the discontinuity is called removable. So let's go back and look at exercises 1 to 6 and see which discontinuities were removable. All right, well, number 1 was continuous, so we'll skip that one. Okay, number 2, f of x was discontinuous. This one is discontinuous. And we just want to see, is the discontinuity removable or not? Well, the limit as x goes to 2 of x minus 5 over x minus 2 is either infinity or minus infinity, depending on if we're approaching from the left or from the right. Okay, so this limit does not exist because it's an infinite limit. Okay, so this is not removable. In other words, we're checking again part B. Does the limit exist? If it's an infinite limit, or if it's an infinite limit, then it's not removable. Okay, let's look at number 3. Now remember, I think number 3 was continuous. No, sorry, it wasn't continuous. Number 3 was not continuous. This one is discontinuous. And remember that the limit as x goes to 2, in this case, does not exist. Because when we took the limit from the left, we got that by substituting in 2 here, and we got 5. When we took the limit from the right, we substituted in 2 here, and we got 9. So they're different, so the limit doesn't exist. Now, so in other words, B is not true, and so since B is not true, we conclude not removable. Okay, let's look at number 4. I think number 4 was continuous, so it's not an issue here. Let's look at number 5. Number 5 is a typical example of a removable discontinuity. Actually, 5 and 6 are typical examples of removable. All right, the limit does exist here. We're looking at part B again. The limit as x goes to 5 is obtained just by substituting into the polynomial. All right, so, sorry, x squared. The limit is 25. So the limit exists, so here we have removable. And in 6, we have a similar situation. The limit exists. Both of these are discontinuous, all right, but in both of them, the limit does exist. Here, the limit as x goes to 1. We take the limit by reducing first. Okay, so the limit is 1/2. The limit exists, so we conclude removable.